For 2,000 years, one material has ruled the entire planet. The Romans used it. Every empire since has been built on it. And for the last 100 years, not a single engineer on Earth could imagine building a city without it. Concrete, cheap, grey, boring, and completely unstoppable. There was just one rule everybody agreed on. You could not fundamentally change how concrete is made. You could tweak it. You could add things to it. But the core process, mix it, pour it, wait for it to dry, that was locked, untouchable. Engineers treated it like gravity, just a fact of the universe. Then a team of Chinese scientists did something that, on paper, sounds almost stupid. They took wet concrete, and they crushed it. And the result was so strong, so dense, and so much cleaner that laboratories in Germany, Japan, and South Korea dropped what they were doing and started racing to copy it. Wait, what? But here's the part nobody wants to talk about. This breakthrough exposes a dirty secret the construction industry has been hiding for decades. A secret about pollution, about money, and about why the smartest engineers alive never fixed a problem that was sitting right in front of them the entire time. Some experts are calling this discovery impossible. Others are calling it the beginning of the end for concrete as we know it. So which is it? Or who? Stay with me, because this story is bigger than one lab, and it starts with a number that should genuinely scare you. Look around you right now. Every road you have ever driven on, every bridge you have ever crossed, every building you have ever walked into, they almost all share one thing. And it is not steel, not wood, not glass. It is concrete. Here is how much of it the world makes. If you poured a single year of global concrete production into one giant river, that river would stretch from the Arctic Circle all the way down to the southern tip of South America. That is not a metaphor, that is just the math. Concrete is the second most consumed substance on the entire planet. The only thing humans use more of is water. More than oil, more than steel, more than timber. After water, concrete wins by a landslide. And that is exactly where the dark secret begins. Because making concrete releases a staggering amount of carbon dioxide into the atmosphere. Not a little, not a rounding error. The cement industry alone, and cement is just one ingredient inside concrete, is responsible for roughly 8% of all the greenhouse gases humans produce every single year. Let that sink in. That is more than every airplane in the sky combined. It is nearly as much as every car and every truck on every road on Earth. Wow! So the obvious question is, why did nobody fix this sooner? And the answer is the first twist of this whole story. It is not that scientists weren't trying. It is that concrete is genuinely one of the most brilliant materials ever invented. And breaking something that brilliant is almost impossible. Think about what concrete does. It is cheap enough that even the poorest countries can afford it at massive scale. It is strong enough to hold up skyscrapers. It can be poured into any shape a designer can dream up. It hardens on its own, with no special treatment. It does not rust like steel, rot like wood, or shatter like glass. And it lasts for decades, with almost no maintenance. For most of human history, no other material came close to offering all of that at once. Engineers love it, because after generations of use, they know exactly how it behaves. Under stress, in freezing cold, under crushing loads. Builders love it because it's available almost everywhere on Earth. City planners love it because once it's in the ground, it stays there. The entire profession of civil engineering is quietly built on one assumption, that concrete exists and that it works the way it always has. But the problem is buried deep inside the chemistry. And you cannot simply engineer it away. To make cement, you have to heat limestone to over 1,400 degrees Celsius. At that temperature, the rock literally breaks apart and releases carbon dioxide as a direct chemical byproduct. Listen closely, because this is the key. That carbon is not coming from dirty fuel. Even if you powered every kiln on Earth with perfectly clean electricity, you would still release enormous amounts of carbon, straight from the stone itself. The emissions are baked into the recipe, literally. Now scale that up. China alone, between 2011 and 2013, used more cement than the United States consumed in the entire 20th century. Not in a generation, not in a decade, in 2 years. Whole cities from scratch. Highways across regions that had never had roads. Bridges over rivers that had never been crossed. For years, researchers chipped away at the edges. Some replaced part of the cement with industrial waste, like fly ash or slag. Others built geopolymer concretes with different chemical binders. A few tried capturing carbon at the cement plants. All of it helped, a little, but none of it changed the fundamental economics enough to go truly global. The core process, mix, pour, wait, stayed exactly the same for over 100 years, and that is when someone finally asked the question nobody had fully explored. What if the problem was never what you put into the concrete? What if the problem was what you do with it the very second it leaves the mixer? To understand what these scientists did, you first have to understand what fresh concrete actually is, because most people picture it as a solid. It is not. Right after mixing, concrete is a thick, wet slurry, packed with water, trapped air bubbles, and loosely arranged particles of cement and crushed stone. Normally, you pour that slurry into a mold, and then you basically wait. Gravity does some of the work. A vibrating tool shakes out a few air pockets. Over hours, the particles settle, the water slowly escapes, and the mix hardens into whatever shape you gave it. This method has not changed in any real way for generations. It is patient, it is passive, and it leaves the material full of tiny flaws. A research team spread across Tongji University, the China Building Materials Academy, and Shanghai Jiao Tong University decided to stop being patient. Instead of letting gravity and time do the work, they applied raw mechanical pressure to the fresh concrete while it was still wet and workable. Between 5 and 15 megapascals of force, roughly the kind of pressure inside a heavy-duty hydraulic press, squeezing the mix from the outside in. And what happened next rewrote the internal world of the material. The particles were forced together so tightly that the trapped water and air had nowhere left to go but out. The concrete became dramatically denser, almost instantly. Picture the difference between a loose pile of sand and a compressed block of solid stone. Same grains, completely different material. Woo! Now here is where it gets technical and important. Inside any piece of concrete, there is empty space, microscopic gaps and voids scattered all through it. Engineers call the total amount of that empty space the porosity, and under this pressure method, the porosity dropped by around 45% compared to standard concrete. Why does that matter so much? Because those tiny voids are where almost every concrete disaster is born. Cracks start at voids. Water sneaks in through voids. Road salt and seawater chemicals travel through voids to reach the steel bars hidden inside, where they trigger corrosion that can rot a bridge from the inside out. And when water trapped in a void freezes, it expands, and it cracks the structure apart from within. So reduce the voids, and you erase most of concrete's biggest long-term weaknesses in one single move. But the real magic happened at a boundary you have probably never heard of. Inside concrete, wherever the cement paste wraps around a piece of stone, there is a microscopic transition zone. And in normal concrete, this zone is the single weakest part of the entire structure, looser, more porous than either the paste or the stone alone. It is the first place a crack forms the moment the material is stressed. It is the traitor hiding inside every slab. Under this pressure casting, that traitor zone tightened dramatically, with up to 35% fewer voids than in conventional concrete. The weakest link in the chain suddenly became one of the strongest. Wait, what? And the lab results were jaw-dropping. Compressive strength jumped by over 80% in the highest pressure batches. Resistance to water, to freeze-thaw cycles, to chemical attack. All of it improved substantially. And here is the part that makes engineers sit up straight in their chairs. The team pulled all of this off without adding a single new ingredient. No expensive additives, no exotic materials, no new recipe. The exact same concrete, simply handled differently, produced a fundamentally superior material. Then they did something almost unheard of in this industry. They published everything. Raw spreadsheets, microscope images at extreme magnification, Force and displacement readings from nanoscale mechanical tests, all of it, freely available to download, under an open license. In a field where methods are guarded like state secrets, that transparency was almost as shocking as the results, because it meant anyone, anywhere, could check the work. And when they did, the real chaos began. While the concrete story was exploding through research journals, a completely different technology was quietly developing in parallel. And this one asked an even more dangerous question. Not just how do we make concrete better, but do some buildings even need much concrete at all? It is called, and it was developed by Broad Group, a Chinese company with a long, strange history of doing things in construction that most people flatly assume are impossible. From the outside, the panels look almost too simple. Two thin skins of steel, held apart by a precise grid of hollow steel tubes arranged in a geometric lattice. Honestly, it looks a little like the inside of a waffle iron, but engineered to a tolerance measured in fractions of a millimeter. The design steals its genius from aerospace. It is the same basic logic that lets an aircraft fuselage be both incredibly thin and incredibly strong. Instead of fighting stress with brute mass, you route it through a structured lattice. The steel skins handle tension and compression. The tube lattice handles bending and twisting. Together, they create a panel that weighs less than a tenth of a comparable reinforced concrete slab, while carrying similar structural loads. And Broad Group had form. Back in the early 2010s, they stunned the world by assembling a 30-story hotel in just 15 days, using modular steel construction. B-Core pushed that even further. The panels are designed to lock together with robotic fasteners, which means an entire floor of a building can be finished in hours instead of days. In one 2025 project, a 10-story building was reportedly assembled using B-Core modules in under 30 hours, and the workers were not even rushing. The system is simply built for speed, the same way flat-pack furniture is built to go together without special tools. But the truly serious advantage is what happens when the ground starts shaking. Buildings in earthquake zones face a brutal problem. Traditional concrete structures are heavy, and heavy things are hard to stop once they start moving. When an earthquake hits, all that mass generates enormous forces the building has to somehow absorb without tearing itself apart. Lighter B-Core structures absorb and redirect those forces in a completely different way. And in seismic testing, the panels handled shock and vibration with a resilience that conventional concrete frames struggled to match. For the billions of people living in the world's most crowded earthquake zones, that is not a minor detail. That is the difference between a building that stands and one that does not. Now here is why these two inventions matter together. The pressure-cast concrete and B-Core are solving different problems, but they point in the exact same direction. One makes the concrete you do use far stronger and far cleaner. The other slashes how much concrete a building needs in the first place. Combine them, and the impact on cost, speed, weight, and pollution becomes far larger than either one alone. And that combination is precisely what set off alarm bells across the entire global construction industry. Here is something you need to understand about construction. News in this field does not travel fast. Building codes take years to change. Giant companies move slowly and carefully, because when you get a structural material wrong, the price is not measured in money. It is measured in human lives. So when international interest in these Chinese methods started accelerating within months of the 2025 publication, that alone was a signal. The industry does not move that fast for hype. It only moves that fast when it smells something real, and a lot of it. According to reporting around the technology, dozens of international patent families have now cited that original Chinese research, with filings traced to Germany, Japan, South Korea, and the United Kingdom. And these are not polite academic footnotes. These are companies and research consortiums throwing legal and financial firepower behind the idea, trying to stake their claim before someone else does. The trials that backed it up were what turned skeptics into believers. On one river bridge project, a stretch of deck built with the pressure-cast concrete was monitored continuously for 12 months, using strain gauges and moisture sensors buried right inside it. The real-world compressive strength averaged around 61 megapascals. almost exactly matching the lab predictions. 0 visible cracks, stable moisture the entire year, and once again, every single data point was archived publicly, free for any engineer on Earth to download and verify. In another pilot, prefabricated B-core wall panels used in a housing project reportedly delivered a noticeable improvement in thermal insulation and needed far fewer repairs after installation than conventional prefab panels. And notice the reason the engineers gave for choosing it. It had nothing to do with looking green or trendy. It was stronger, it was cheaper, and it came with data. Because in the end, what is really driving the world to copy this is not idealism. It is cold, hard math. In regions where carbon emissions are taxed or capped, cutting cement use translates directly into lower regulatory costs. And in any market on Earth, if you can slash the price of the most expensive ingredient in your product, while making that product stronger at the same time, that is not a trend. That is a weapon. As one research executive reportedly put it, this is not about following a movement, it is about staying in business. So then why are some engineers still calling it impossible? Because for 100 years, the textbook said the weak transition zone could not be meaningfully fixed. The textbook said porosity at that scale was just the price of using concrete. The textbook said the core process was final. This research did not tweak those rules. It broke them. And when a result violates what an entire profession was trained to believe, the first reaction is never applause. It is denial. The impossible label is not an insult here. It is a confession of how big the shift really is. Now let's talk about the number that sounds insane, until you remember how much concrete the world actually pours. Life cycle models suggest that switching just 30% of new structural concrete worldwide to this pressure casting process could cut annual carbon dioxide emissions by around 850 million tons. Let me put that in human terms. That is more than the entire country of Germany produces in a full year. From every power plant, every factory, every car, and every farm combined. One change, one process, applied to less than a third of global concrete, delivering a climate result the size of an entire industrial nation. Wait, what? But this is where I have to be honest with you, because the story is not finished, and the road ahead is genuinely hard. Turning a brilliant lab result into a global standard is a long, brutal climb. Building codes in most countries update on timescales measured in years, sometimes decades. And they move slowly on purpose, because the cost of a structural failure is not just financial. So every country that wants to adopt this at scale needs its own independent testing under local conditions, its own regulatory approval, its own trained workforce that knows how to run pressure casting equipment correctly, every single time. China can hand the world the blueprints, but the rest of the world still has to do the work of adapting them. Then there is the machinery itself. Pressure casting needs equipment most concrete plants simply do not have today. Retrofitting old factories or building new ones is a serious capital investment. For big construction firms in wealthy countries, that cost may pay off fast, thanks to the savings. But for smaller builders in developing economies, the barrier could be much higher. And that raises an uncomfortable question. Will this technology actually reach the parts of the world that need affordable, low-carbon building the most, or only the places that can already afford anything? None of that changes what the science shows. It just defines the gap between what is now technically possible and what will actually happen in the real world. And closing that gap is not really an engineering challenge anymore. It is a challenge of policy, of money, and of political will. But step back and look at what has already changed. For the first time in a very, very long time, the fundamental process of making and using concrete is genuinely shifting. Not at the margins, not just in a laboratory, but in real bridges, real buildings, real structures that real people are standing inside right now. That is new. And remember, concrete is the second most consumed substance on Earth, with only water ahead of it. When something like that starts to change, it does not stay small for long. So here is my question for you. If a breakthrough this massive was sitting right in front of the world's smartest engineers for over 100 years, hidden inside a process everyone assumed was finished, then what other obvious, world-changing breakthroughs do you think are hiding in plain sight right now? Drop your answer in the comments. I read them all. And if this changed the way you see something you walk on and live inside every single day, hit that subscribe button and turn on notifications, so you never miss the next story the world wasn't paying attention to.